looking for the volunteer. Mike, volunteer.
Good afternoon, everybody. I think it's time to start. So welcome all of you on this Jaszowiec 2026 school, which precedes the conference of the same name. And let me begin with some kind of introduction. So I am Michał Baranowski from Wrocław University of Science and Technology, and I have a privilege and pleasure to chair this session and organize this tutorial session. So let me first thank you all of you for being here. And at the beginning, I also need to acknowledge some important people who make this event possible. So first of all, the chair of the conference, Piotr Perlin, together with the secretary, Anna Kafar, and of course, the very important person, our organization committee, who really makes these things possible with the great lead of Ania Reszk. And of course, this event is not a single event, and it is not made by the single institution. There are plenty of institutions across Poland involved in the organization of this school and also the whole conference. Probably you know all of them. So most importantly, this is University of Wrocław, Wrocław University of Warsaw, Wrocław University of Science and Technology, Unipress, and Polish Academy of Science Institute of Physics, and Łukasiewicz Institute. And from this year, we have also the patronate of the Ministry of Science and Higher Education, which probably means that our event is kind of important in Poland. So we are very grateful for this acknowledgement. Sorry. Yeah, and of course, this is the scientific conference, and probably you know that we can work more or less with the curiosity and coffee. However, the conference needs some further support, so we have our sponsors who provide us some material support, which really help us making this event even better. So we are also very grateful for all this company for supporting this nice meeting. And going to the main topic, our goal or aim of this school is very simple. We would like to expose you to some new concepts in semiconductor science and solid state physics. Obviously, saying simple doesn't mean that it is very, very easy, but fortunately we have 4 great speakers which will guide us through some very interesting topics. And today we will start with Alexei Chernikov from the Dresden University of Technology. And Alexei will explain us how excitons or optical excitation propagates in 2-dimensional semiconductors. And this will be all for today, but we start early tomorrow morning, and we will start at 9 a.m. with the talk of Professor Rachel Olivier, who will show us how we can understand something about the gallium nitrides and nitride semiconductors using different flavors of the microscopy. And then we will move to Professor Sebastian Klempt from University of Würzburg, who will address the topic of topological photonics, and which somehow brings the concept from advanced condensed matter physics to light and allows to control the slides in a very interesting way. And after this three, let's say, experimental tutorials, we will move to the theory part, where George Volonakis from University Deren will explain us how the density functional theory work, and probably equally important, how this can be used for something practical, and how to predict and design materials using this theoretical approach. With that, I also need to provide you with some organization information. So we were supposed to have a campfire today to join you, to integrate you. Unfortunately, the weather is not very nice. So our campfire will change into the grill in a grotto. For those of you who don't know, the grotto is a kind of chamber just behind the hotel reception. And so there will be today dinner. Then, of course, we will have another important thing tomorrow, which is welcoming with a glass of wine, and we will have a concert. And now some more practical information. If you don't remember the program, you have to remember that it is all written here, so you can always have a look. And another very practical aspect, please don't make a coffee during the presentation. We would kindly ask you. There will be a break during the lecture, so then this is the time when you can take your coffee. But hopefully it will be not needed because the talks are so exciting. And in the end, to conclude, please be active. The speakers that we have here, they are here because they want to share their knowledge. Try to use it. Ask a lot of questions, discuss with them, maybe challenge their ideas, and most importantly, enjoy this event. Thank you for your attention, and Alexei, the floor is yours.
All right. Good afternoon, good evening, everybody. I'm very happy to be here. Jaszowiec is actually one of the conferences one hears quite a lot, and then there's finally an opportunity to participate. So many thanks to Michał and the whole organizer team for making it happen and making really exciting program. And I'm particularly honored, and of course it's always a bit of a challenge, to kickstart this event. So the menu for today is what I called in a little bit of a technical way, transient microscopy, but the talk itself will be largely about the transport of optical excitations. Yeah? So usually if you think about transport, we think about electrons, but in this particular case, it will be about excitons, about optical excitations. I will take two-dimensional materials as example, and in the first part, we'll discuss a little bit about excitons and 2D, but for most of you, maybe for all of you, it will be nothing really new, just a bit of a recapitulation, and then we'll discuss optical methods, how we measure their propagation. I give you a few examples, and then somewhere towards coffee break-ish, somewhere here maybe, we'll discuss propagation regimes and then go to maybe slightly more advanced topics. Again, depending how fast we proceed, how many discussion questions we have, I'm also happy to skip some parts of it towards the end. And we'll definitely be happy to answer questions also during the presentation. Okay, so if there is an opportune moment and you want to ask me something, so please go ahead, just raise your hand. And I try to catch you because the NA is here relatively broad. If you don't ask questions, don't worry, I will ask you questions. Okay, so anyhow, there will be questions. All right. Maybe one last disclaimer. So while I'm choosing this particular material platform, yeah, a lot of the concepts are, you know, for some of you in the audience, also very familiar. The field of exciton transport did not start yesterday, but a lot of these concepts, as I hope, will also be applicable for systems that are different from the ones that I present. Okay, so enough of that. Let's start to just consider a generic low-dimensional system. You can think about your favorite quantum dot, nanowire, 2D systems, quantum well, van der Waals, semiconductors, what's not. And then we know that when the photon arrives, an electron-hole pair is created. And in most of these cases, these electrons and holes do not exist by themselves. They're not independent from each other. In fact, they're bound, and sometimes quite strongly, by Coulomb interaction. Yeah? Which means that this is usually the state that matters. This is called an exciton, which represent fundamental optical excitation in materials, and which is also, as we'll see, the main carrier of energy, and in some cases also of quantum information. Now, again, in this case, I'll focus on 2D, but some of these concepts definitely would apply to some degree to 1D, 0D, maybe a little bit trickier, but we'll focus on something that evolved from the physics of quantum wells and two-dimensional semiconductors to the modern research directions. So if you consider a material such as transition metal like chalcogenides, maybe a quick show of hands, who is working with this class of materials, van der Waals crystals? Okay, a few. Very good. Who is working with this class of systems, metal halide perovskite, in 2D or 3D form? Also a couple. Okay. Those who work on neither, don't worry. Again, what I want to present you will apply to other material platforms as well and have applied to them in the past. Now, the first question to you. If you think that this is, the exciton is a fundamental optical excitation, what can be an observable to convince yourself about it? And don't worry, if nobody raises a hand, I will just pick a couple. Yeah. So no PIs, just students. So what you would look at, who is doing optics? Who is doing spectroscopy? Spectroscopy, yeah, no, hands up. I saw a hand here. You, who else? Okay, so maybe the two gentlemen, you're doing spectroscopy? Yeah, you can help each other. How would you convince yourself that single electrons are not enough, that you have an exciton? Which type of experiment you could consider? And you don't have to say your name, you know, it can be like anonymous and stuff.
Can you repeat the question?
Excitons, how you show that they are there?
You just look at it, like...
Yeah, how,
inside.
spectroscopist? What do you do? What do you do? How do you look at it in the spectrum? What are you looking in the spectrum for, if you're looking for excitons?
Well, an energy gap, for example.
Sorry, well, energy gap, there was something here? Reflectance, okay, what do you expect to see? So reflectance was, I just repeat, don't worry. Yeah? What do you expect to see in contrast to free electrons? Which type of shape you expect? Lorentzian, yeah, some form of a...
Luminescence, a Lorentzian up, and reflection, a dip.
Yeah, a dip, a peak, something sharp, something like, you know, quasi-atomic. In fact, indeed, you expect something like this, because free electrons in 2D, for example, they will give you a different line shape. Yeah, they will give you steps for the quantum well, but every time you see a peak, in case something like Van Hoff singularity is absent in the system, yeah, so one needs to be a bit carefully, but every time you see something like this, it is enough to look at something like optical absorption to convince yourself that non-interacting electrons are not enough to describe the properties of the system. Yeah? And of course, there are much more complicated experiments to demonstrate. Now, the excitons, as you see, you know, it's a very recent topic. So Jakob Frenkel predicted it in 1931, right? So this is almost 100 years ago. And in this paper, as you see, he was concerned about excitation that is not confined to a particular atom, but diluted between all of them in the form of exciton waves. And here he's talking about heat transport in particular. And then, in principle, the experimental demonstration that is accepted as the evidence of the exciton happened 20 years later, right? 20 years later, where people were looking at basically atom-like states of the excitons. And this is a picture of a so-called Viney exciton that is still true to this day. Yeah? So if we turn to 2D, yeah, so we go from bulk material, that by the way was cuprous oxide, that's very famous semiconductor to look for excitons. But if we go to a system like this, what do we need to take into consideration to properly describe Coulomb interaction? What do we need to consider if we go from bulk to a low-dimensional system? Anybody who's laughing can volunteer with the first attempt. In a low-dimensional systems, what should we consider as a, for example, quantum mechanical phenomenon? Yeah, try. Remember your solid state physics courses, you confine something, so what do we need to consider? Dielectric constant, that is exactly the opposite what I wanted to try to ask you. But indeed, we need to consider dielectric constant. Why? Why? Can you explain it a little bit?
Because exciton is delocalized.
Exactly, exciton is delocalized, correct, right? So you imagine you have a field between these two particles, between electron and hole, so you need to consider dielectric environment. This is very important for any nanostructure, correct? And then what else on a single particle level, but which will impact exciton binding energies? What else do we need to consider if we go from 3D to 2D? Yeah, mass, always important, but what else? I'm looking right here, this part of the audience was not addressed just yet, so I don't want to ignore you. What do we need to consider in terms of electronic properties if we reduce dimensionality? Energy levels, very good, yeah. No students, right? You already more experience, probably. Yeah, so if you confine something, you have an extra density of states changes, the quantum confinement as a general phenomenon. These are the two ingredients if you think about excitons in low-dimensional systems. You start with quantum confinement. What you see here is, by the way, solution of hydrogen equation in 2D, because people for some reason did it in the 50s, you know, just why not? Let's calculate. There is an analytic solution, and then there is a dielectric effect. Yeah? And if you look very carefully, and if you want to be very quantitative, what you need to consider for the description is the fact that the screening and the dielectric property that you mentioned is different inside the layer and outside of the layer. Yeah? And that leads to certain phenomena that are not so important for this talk, but something that gives you, for example, wave functions of excitons. So this is something like a radial probability. You fix a hold at 0, and then you look where the electron is. And here already you see that the excitons in this type of structures, when they're strongly bound, they're quite small. Yeah? So we're talking about distances on the order of nanometers, but they're still reasonably extended across the lattice. And we'll talk about the implications of the exciton size for its transport. Okay. This is just a quick slide to show that whenever we have Coulomb interaction, not only excitons exist, you have usually a number of complexes that can all be mobile. Yeah? The excitonic collision, you have particles called trions or fermipolaron. This is when excitons interact with free carriers. You can have excitonic molecules, and then ultimately at some point the excitons will cease to exist if the density is too high. In the context of semiconductor physics, as many of you know, this will be called a Mott transition. Yeah? And the energy scales here are related to the van der Waals semiconductors, transition met dichalcogenides or two-dimensional perovskites. So because excitons are carriers of energy information, therefore it's very natural to ask oneself, okay, how do they move, right? How do they transfer this energy, how they transfer this information? And one can have very different ways how a particle in principle can move, yeah, such as an electron or exciton or whatever. Hopping, semi-classical transport, these are the ones we will discuss also in this lecture. These are also the ones that are mostly encountered. Ballistic transport is probably the simplest version and the one that is, you know, rarest to observe. And then there are interesting phenomena, hydrodynamic regimes and quantum interference. We'll touch a little bit on this one for the weak localization, and hydrodynamics we shall not touch here. Interestingly, look at this paper, 1938. This is reportedly one of the earliest, if not the earliest paper where people asked themselves about transport of excitons. 1938. It's also interesting to look at the authors, James Franck, Edward Teller. Yeah, Edward Teller of trying to convince Oppenheimer to build hydrogen bomb of fame, among other things. So this is not the work Edward Teller is most known for, but these are the two people who wrote the paper with the title Migration and Photochemical Action of Excitation, Energy in Crystals, and they also use the term exciton. Now, looking at this title, and maybe some of you know, what do you think was the motivation? Think about the introduction. You write such a paper, maybe already in the 30s. How would you motivate? Why should one look at this? Why can this be important in nature? How energy migrates through a crystal? Which type of processes could be relevant? Because thermodynamic, but in which way? Maybe you can explain a little bit. We need to motivate it, right? Because if we're not motivating it, then we can go and drink coffee and have a nice evening. If we cannot find motivation to look at exciton transport, why bother? Yeah, I mean, I'm serious with you. So how can one motivate transport of energy in crystals? What do you think? What are the options? Maybe from today's perspective. Why do you want to consider energy moving in crystals? Think about technology. You guys try. Technology. Why do we need energy transport? Which application may come to mind? Context of optics, maybe. Light comes in, energy needs to go somewhere. What am I describing? Somebody can help, right? I don't want to put you on the spot. Sorry? Communication, yes. I mean, this is more towards information transfer, but yes, what else? Photovoltaics, yeah. You're not a student, but still correct. Oh, it was your, oh, I'm sorry. Oh, big mistake. Photovoltaics, indeed, right? But back then, interestingly, again, 1938, we're here in the School of Semiconductors, but the motivation was photosynthesis. In the plant, I mean, that's how the plants live, right? This is the process. This process requires understanding of energy transport, which is also in the plant mediated, here you are, by excitons. Yeah? So the questions were motivated from biological perspective, of course, later on. Here you have example from the 80s. Here's the example 2005, and the way we have one of the co-authors here, David Snoke, at this conference giving a talk next week, when people really looked at the more modern versions of the material platforms, so not that, didn't consider plants theoretically, but looked at quantum wells, double quantum wells, looked at diffusion and transport in this type of structures. So it's a very broad field, in no way confined to the more modern classes, let's say, of materials that people are studying, van der Waals semiconductors, perovskites, and such. So how to measure exciton propagation? What is the main challenge in contrast to electrons, if you think about transport? What is the main challenge if we go from measuring transport of this or transport of this to a transport of that? Yes? Small distances, well, you never know, right? You can say excitons, who knows, maybe they will travel for microns or maybe even millimeters. Definitely the case in some of this, cuprous oxide / gallium arsenide. But if you think about the measurement challenge. Sorry? But maybe you can explain, so don't prompt me, just... So how do we measure transport of this? Yes, full sentence, please. Measure the current, apply the voltage, right? Apply electric field, thank you very much. What is the problem with that particle if it's strongly bound? What will happen if we apply electric field? It's neutral, exactly. This is the biggest challenge, right? It's neutral, so in principle you can say at a contact, you can separate them, but in general it's a neutral particle. How do we measure transport of neutral particles? How would you do it at home? If you, for some reason, were curious to do it, what type of technique you can come to mind? You are not wrong, but this is not enough. Yes? But you need to involve some form of excitation and some form of a field that is not electrical, so you consider for something like this, like a strain field, for example. But you also can look at free diffusion, right? You can do an experiment, and this is, now I'm not doing experiments anymore, really, but this is one I did. A drop of water, a drop of color in water, and then you observe how it diffuses, right? This ink is not electrically charged, you just observe free propagation. And this is the concept that we can directly apply to measuring transport of excitons. Yeah? We need to adjust the setup a little bit, so ideally use optical injection, fast. The imaging needs to be usually submicron, I will show you. So we're talking about hundreds of nanometers, micrometers. These are the time scales, very often relevant. And also the time resolved detection need to be much faster than just making photographs here with a camera. Yeah. So the general scenario you can consider like this. A local optical excitation creates excitons. They will diffuse and propagate over some distance in time. And then one needs to find ways to monitor exciton density as function of space and time. And this can be done by different means, and I will show you. In the end, what one wants to do is to analyze the profile, right? So again, remember this ink in water. You're looking at the shape of the exciton distribution, and you want to know how it changes in time, how it broadens. Maybe in case of a current, it will even shift. Yeah? But this is the analysis of the data. This is the data that one needs to consider. Here, for example, you have two cases, 0.1 nanosecond, 1.5, and then you see a small broadening that can be analyzed, usually fit by some peak function. Gaussian is good enough. And then look at the changes of reflection, yes, still powerful, transmission scattering, or photoluminescence, yes. And there's a variety of approaches. Here it's a nice paper, relatively recent, by Naomi Ginsberg, will still outlining these techniques and the capabilities and technical requirements to perform this type of experiments. And then, of course, one can start changing, heading contacts, heating it up, cooling it down, and as it is with transport of electrons, changing external conditions. The first type of technique, very quickly, it's a differential absorption-based measurement. So here the ideas, and many of you will know, and some of you are doing it for sure. You perturb a system with a strong pump that will create excitons, and then with a probe that is offset in space, delta x, and time, delta t, you will probe the local changes of permittivity as function of these coordinates. For the experiments, but maybe also theorists in the room, how do we change delta x and delta t in experiments if we have two pulses? What do we use to change delta x? What do we use? Well, spectroscopists. Who is doing pump probe? Anybody doing pump probe? Perfect. So, how do we change delta x? Please. Yeah, delta x. How we change delta x? Just move the mirror, exactly. Just move the mirror. Yeah, as simple as this. And how we change delta t?
Check the delay line, the optic distance.
Exactly. Exactly. So in both cases, to change both of these parameters, this can be done mechanically and externally. We don't need additional equipment. We just make sure that the light takes different paths, either delayed in time or delayed in space. That's it. That's a principle. Of course, the reality of such experiments can be much more complicated, but this is the idea. This is the type of responses you can expect. So in this case, what is plotted is absolute reflectance, and then how, for example, it can change as a function of time. So here, for example, the pulse comes. There are strong changes in the line shape. It can be broadened. It can be shifted. It can bleach. Yeah? So the area can be reduced. All of these changes can happen. To explain these changes typically requires either certain assumptions or complicated models. But in principle, you can relate any of these changes in some way to the local exciton density. Yeah? But not only excitons. Alternatively, one can use luminescence. So here, you just use a single pulse just to create the excitons, to create optical excitation. And then as function of space and time, one will look at the light emission. Yeah? So the photons will give you a trace where were the excitons at a certain moment and at a certain distance. Imaging of luminescence is usually necessary, so you're really looking at a real space picture. Time resolved detection, and technologically it can be done with a fast diode. Time correlated single photon counting has some advantages in terms of timescales and sensitivity. One can use a streak camera, count single photons, and in the end have a spectrum, for example, like this. Who is working again with transition metal like alkogenide? Hands up. You. Okay. What material is this? Can you recognize the spectrum? It's fine if you can't. Low 5 Kelvin, 5 Kelvin. That you can see because the lines are so narrow. It cannot be room. Tungsten diselenide, and how do we need to prepare it to get such a spectrum? Exfoliate and encapsulate. Very nice. Thank you very much. Indeed, you're completely right. A professional recognizes monolayer of tungsten diselenide at 5 Kelvin encapsulated by HBN, and we will come to the consequences of encapsulation also in transport. Yeah? But this is a type of spectra that you would then image, or this type of luminescence image on your detector, and then look at the expansion of the spot. Okay, and for example, get a data like this. So here you have, as a function of time on the left side, how the luminescence decays. So what you see with your eye is mostly a decay of luminescence, because again, the particles are metastable, excitons do recombine, they have a finite lifetime. And on the right side is the data shown when you normalize each profile at each time step, and then you can, even with your eye, see the very small but visible broadening, yeah? So how the excitons propagate. Now, if we summarize the advantages, so maybe we start with somebody who is doing pump probe. What are the big advantages of a pump probe technique? I mean, there are many, but can you name us a few? Yes?
Pump is modulated and filtering out the noise.
Yeah, noise. You can have high signal to noise if you want. What else? I mean, it's not only noise. Anybody else? Pump probe? What is it known for? As a capability? High temporal resolution, exactly. High temporal resolution is one of the things that comes to mind. Indeed, this is the method to use if you want to have, let's say, sub 100 femtosecond. And another point, even in a dark material, technically, dark in the sense that the quantum yield is poor. Yeah? It doesn't emit light. You can still do a pump probe experiment, and there are many good examples for this. What are the disadvantages if you do pump probe? Or what can be disadvantages? What do one need to consider? Because otherwise everybody should do pump probe. No? What could be disadvantages of this type of measurement? Laser power can fluctuate. I mean, this can be a problem anyhow, but what about the absolute laser power on average? Do you require more or less with respect to luminescence experiment on average? Depends. Pump probe measurements, sometimes, I mean, it's hard to do with very low powers. It's hard to do with very low powers, and the reason is you can much easier count single photons, yeah, for very low power excitation, then detect changes, even if you can play around with tricks like differential detection and what's not. Also something important, whenever you look at some trace in pump probe, and you will see papers with those traces like a transient, the fact that this corresponds to the presence of charge carriers is the interpretation of the authors. Yeah? It doesn't have to be wrong, in many cases is it correct, but many types of non-linearity, for example, presence of phonons, magnons, whatnot, can change a pump probe response. A pump probe response can be sensitive not only to excitons but to other particles. This ideally should be yellow. So it's not necessarily a disadvantage, but this is something to consider. Now, advantages of luminescence in this case. One can have quite high sensitivity, so you can perform luminescence experiments time resolved under almost homeopathic conditions of less than 1 exciton per pulse because of the single photon detection capability of modern detectors. Dark states, in a sense, states which do not have strong oscillator strengths can be detected if they are low-lying states. And the response in many cases is exclusively excitonic or electron-hole pairs, but the disadvantages are, on average, lower time resolution, and typically quite bad because it depends on quantum yield. So if you have a material with a lot of non-radiative channels, it can be tough to measure luminescence. Regarding the analysis of the data, so let's say we acquired the signal, be it in pump probe, be it PL, then, for example, this would be the extracted quantity. It's called mean square displacement, MSD, but in principle it's a variance of the Gaussian that you use it to fit. And then you have characteristic regimes. If your area, so this is the square of this, yeah, you see the square, the area increases linearly. In most cases, this means you have free diffusion. There's a few exceptions, but we'll not discuss it here. If you have a question, we can talk later. But if the area grows linearly, then you are in the regime of free diffusion. Ballistic transport would look quadratic in this plot, so the area will increase quadratically, yeah, because then it means that we have a fixed speed of the particle. And there are many cases where you see subdiffusive behavior, which means your speed of the expansion is time dependent. Yeah? And these are kind of general regimes that you can find in this type of measurements. And sometimes it's also useful to define an effective diffusion coefficient, which may also be time dependent by just taking a derivative, sorry, a square is forgotten here. Oh no, sorry, it's wrong, it's fine. So you take a linear, the first order derivative to determine the effective diffusion coefficient. So with this, we're done with the first part about measuring exciton diffusion, pump probe, time resolved luminescence, our techniques of use, and then the evaluation of exciton density at the position x and time t is the relevant quantity. Now to the examples. The first one, and the first is usually, always probably because you never know, but for van der Waals materials, yeah, because the other materials you go back decades ago, but for van der Waals materials, this paper, about exciton diffusion in monolayer bulk MOSC2, here people use the pump probe setup. So this is a typical way how it can be done. So there is a pump which goes through a microscope onto the sample. The colors are obtained by photomixing. You have a probe that also impinges on the sample, and then in principle you can use this mirror, for example, or that mirror to control the spacing between the two, and then there is a delay line somewhere in between that will delay one pulse against each other, and then the detector, and this is the type of data you get. So here, on this type of data, each measurement point corresponds to a fixed position of the probe, fixed delay, so all the mechanics are set, and then the measurement is done and the signal strength is evaluated. You see a decay of this curve over time, and now one can evaluate the broadening. And if the broadening is evaluated, in this particular case, you get a diffusivity coefficient of 12. We'll talk about a bit later what this numbers means, but it seems that there is a linear diffusion at room temperature for this monolayer material. So the observation here is that excitons in this particular case are mobile at room temperature. Yeah? That's what it is, and then one can think about what the diffusivity actually implies. Quite important parameter, and sometimes this is the one, and I will show you an example that can be measured, is diffusion length. It's defined diffusivity times tau, sometimes there is a 2. That more or less tells you on average during the lifetime of the exciton how far do they travel. Yeah? And in some materials this can be as short as tens of nanometers. In some materials it can be as long as many micrometers, or in some cases even millimeters. When we look at this type of semiconductors, and this is a result, because it leads me directly to the next example, of what actually happens when you encapsulate it. Yeah? What happens when you encapsulate a material, in this particular case, in hexagonal boron nitride. So you see a sharpening of the lines, and sometimes you can have a generic explanation, the encapsulation protects us from the environment. Of course, for a van der Waals system, you can also question why does it need protection, because the surface is largely inert chemically. But this is an observation that leads, at least in this field, to a relatively standard procedure of what do we do with the crystals, how do we get narrow optical lines, place two HBN plates around the monolayer. And the reason why it works, so one of the reasons why it works is the following. This is a schematic, but usually, even if I present you this PowerPoint physics, your environment is not homogeneous. Yeah? If you place a material of any type of substrate, the substrate will have some morphology, some changes of its height. The material will not exactly follow it. So, there will be holes and there will be parts where it's in close contact. You can have adsorbates on top. You can have some polarizable impurities in the material. So the epsilon, this dielectric screening, is not constant. Why does it lead to disorder? Why would that lead to energy disorder? Why should we care about epsilon not being constant as a function of space? What depends on epsilon in low-dimensional materials? You can ask an experienced theoretician. Dielectric screening, yeah, this is epsilon, but what changes when epsilon changes? Binding of the exciton, and now I can go a little bit more advanced. What else changes in terms of electronic transition? Binding of the exciton and band gap, yes? Yeah, so GW, sorry, I'm out of my element, but this is what it does, right? Band gap changes and exciton binding energy changes. Yeah, so you have dielectric disorder will impact free carriers, it will impact excitons, it will obviously impact transport, and this is also what is observed. So in this case, the transport is relatively slow, But if one makes sure that the dielectric environment is constant, the band gap is flat, the exciton binding energy doesn't change, and the transport becomes very fast. Yeah, the change is almost factor of 30. And now we can talk a little bit about the numbers. So this diffusivity at room temperature can always be converted in effective mobility. This is the so-called Einstein relation. There are certain limits where it should not be used, but in many, many cases this is applicable. So if you measure diffusivity, if you measure free diffusion, you automatically know how the particle will react to an external field. Yeah. And if some of you is missing the electric charge here, or is wondering why the electric charge is here, is because very often in semiconductor physics, we're used to use electronic mobility, which is defined as a drift speed versus voltage, but you can define drift speed versus any type of potential gradient, be it strain or what's not, and this will be this quantity. Yeah? So in this particular case, diffusivity of 10 corresponds to effective mobility at room temperature at 400, corresponds to 20 nanometer mean free path, which is quite a lot, and something like a few hundred nanometers of diffusion length, which is, however, is determined by the lifetime of the exciton. And one needs to make some assumptions. One can make some assumptions to get these numbers about the type of transport, and this will also be a topic a bit later on. There is also a version where you do this analysis without time resolution. I'm just showing it to you because this is something that is done quite often without a time resolution in the given experiment. What one can do, one can look at PL, measure diffusion length somehow, yeah, just see how big your PL spot is, and then perform an additional measurements of the recombination time. Yes, and that will give you the diffusion coefficient. So these are two different experiments, and then you get the diffusion coefficient. If this technique is used, one needs to pay a little bit more attention to the proper focusing, to the fact that chromatic aberrations don't play a role, and of course that the time resolved measurement and the time integrated measurement are performed at equivalent conditions. And now I want to show you this observation. This directly relates to this question of disorder. Yeah, so the blue points show data from a material with very slow diffusion, and it has a very long lifetime. And the red data points show encapsulated material, which exhibits very high diffusion because the disorder is suppressed. But now the lifetime is short in HBN. What can be a reason? What can be a reason to find such a correlation? The faster the excitons move, the shorter they live. Yeah. From human experiences, sometimes a relatable observation, but what about excitons? Yes? Yes. Sorry, they collide with something and?
If they are faster, there's higher chance that they will collide with something.
But if they just collide, let's say, if they collide, their momentum is exchanged. So that would affect diffusivity, but not necessarily the lifetime. So what will affect the lifetime? What do they need to encounter during propagation? Sorry? Each other. Oh, this is a good point. We're not at the nonlinear effects yet. So wait a little bit. But what is in the real material that carriers and excitons will encounter that will affect the lifetime? Okay, now I need a lot of hands. Okay, you're working on materials. Not the theoreticians maybe, but the experimentalists. What do you have in your material that determines lifetime very often? Defects, yes, defects, yeah. Materials are usually full, or there are enough defects, there are non-radiative recombination centers in most materials, yes. You can grow very clean materials. I don't want to, insult anybody. You can grow very clean materials, but in the majority of cases, there's somewhere a non-radiative state, right? So somewhere a chair is missing, it's a vacancy, and if I propagate towards this vacancy, I will recombine non-radiatively. So, and what it means is, if the exciton is slow or even localized, right, then the probability of it to getting there, or it takes more time. If I'm slow, it takes much more time for me to random walk towards this defect. If the diffusivity is high, then it's much easier and much more probable to quickly find such a region of non-radiative recombination, recombine. And this is an observation that you can see in many systems when you have not necessarily dielectric disorder, alloy disorder, that if something is fast, then it may find a non-radiative state much quicker. All right, so fast diffusion can mean short lifetime. Yes?
Are so scattered because I would expect that the points for HV encapsulated samples would be like localized on this graph.
Okay, maybe a little bit of a dirty secret of encapsulation, but should not be a secret. Who encapsulates? Who encapsulates things in HBN? You do, right? Okay. So if somebody tells you encapsulate the material in HBN, does it mean you immediately suppress the electric disorder and everything is perfect?
No.
No. What will you see if you look at the sample?
Some interface bubbles. And
Exactly. You can see bubbles, yes, because all the stuff that on the surface bioencapsulates and get pushed into bubbles, the contact doesn't have to be close to each other, and there is, of course, a scatter just from the measurement itself. Yeah? So it means that, and this is the way how this community often handles it, that if you see flat regions with narrow lines, then you can be quite sure that the disorder is largely suppressed, but the pure presence of HBN does not guarantee it, yeah? That the interface is clean. And this is one of the reasons why it scatters. Yeah? And then you can, of course, think, okay, maybe there are other phenomena, presence of recharges, maybe strain inhomogeneity that affects it. Okay? Good. So we are close to a break, but close. Because before this, I want to show you a little bit and discuss with you propagation regimes. Okay? So basically, in which way a particle can propagate, and in principle, again, you can have different modes of transport. The hopping and the semi-classical ones is the one I want to focus with you on. So semi-classical means more or less like, you know, a random walk. Yeah? So ballistic propagation for some distance, you have a random scattering event, your momentum is exchanged, and then the particle propagates in some other direction. So you have a momentum relaxation time or scattering time tau s. And on the other hand, for example, you have hopping. So here it's quite faint, but it means that exciton is localized at a certain spot, and then from time to time there is a hopping process, maybe a tunneling process. Okay. How should temperature impact these two modes? How can we use temperature to distinguish the modes of propagation, be it exciton, be it electron? What do you expect? How should temperature, for example, influence this process? Sorry? So temperature increases, and what happens? Nothing. No. You get some thermal energy into the system. So is a hopping more likely or less likely? More? Who thinks it's more likely? Who thinks it's less likely? Who is too cool to raise a hand? Yeah, more likely. Okay, you have thermal activation, that's here. What about this one? What about this one? That's a tricky one. But how does scattering time changes with temperature? Sorry? Shortens. Okay, shortens. Because of what? Phonons, okay. Now, harder question, if we have linear acoustic phonons. Yeah? Linear acoustic phonons. And now, maybe don't think about the time, think about the scattering rate. How does this rate increases with temperature for linear acoustic phonons? On average, in most systems. As a function of temperature. Try to get the word as a hint. Linear acoustic phonons. Yeah. The Debye model, solid state physics. Initially, the rate increases linearly. And for optical, what is the dependence there? Einstein model. How does the occupation of an optical phonon changes with temperature? Sorry? No. Exponential, exactly. Exponential, yeah. So this rate initially increases linearly, and then at some point there is a nonlinear, a superlinear contribution, and that leads to the following characteristic dependence. On the left side, you have something that is typically expected for semi-classical propagation. Initially, you should not see any change in diffusivity as function of temperature because, as you see, kBT on the top, the thermal energy drives the diffusion. Yeah, so the diffusivity increases linearly with temperature, but if the scattering time is 1/T, then these two quantities cancel each other out, so you have something constant, and then at some point the scattering wins over, so it's basically something like a metallic behavior. Yes? So if you heat up the system, then the scattering process increase. On the other hand, here initially you have this exponential thermal activation. Yeah. And this is an example, an experimental example of hopping. This is a monolayer WSO2 with a lot of disorder, and that's what you can see. First of all, the numbers are very small, and then the diffusivity increases as the temperature increases. Yes, please. It's a dangerous one.
For low temperatures things, the scattering rate of electrons is not determined only by phonons. So how is it in, so impurities, charge impurities start to play the role. What is about the excitons?
So this is correct, but here we can use still, in this particular case, we're still in the semi-classical regime, right? As for depending on the number of impurities. So what you have then for electron as well as for excitons, you have a scattering channel that is, in this basic approximation, independent of temperature, which means that this tau s is, or the scattering rate is a sum of the scattering rate from linear acoustic phonons and the impurity scattering. What it will mean here, and this you can see sometimes even in very good quantum wells from the 90s, grown by famous people, you can still see if you go to very low temperature, in reality, what will happen is you will have this behavior, and then if you go to very low temperature, this will drop again, but not necessarily because of localization, but because of the scattering. This is very important, so thank you for mentioning this. Yeah? Okay, let me look at the time. I think it's fine. We can quickly finish this part. This is free propagation. This is an example from perovskite. So here you see an increase of temperature, and then the diffusivity decreases. And then, on the other hand, at low temperature, you can have a behavior that can be associated either with localization or with additional temperature-independent scattering channel. And the semi-classical description one can also use to try to connect the scattering rates to the diffusivity. How can we try to access exciton scattering optically? If we're interested in this tau s, what type of experiments come to mind? If we try to find out the scattering rate of excitons with phonons, impurities, electrons, what do we need to do? Sorry? Measure dephasing. This is the best way to do it. How do we measure dephasing? With coherent spectroscopy. Yeah? Coherent spectroscopy, depending how you do it, is not trivial. Luckily, people do it, yeah, like 2D Fourier spectroscopy, four-wave mixing. There you can get a dephasing rate. If you don't have access to it, and you have a good sample, how can you estimate the dephasing rate without doing coherent spectroscopy? And those doing coherent spectroscopy, please close your ears, because it will be a bit heretical. But in practice, it can work. How can you estimate dephasing if you don't do coherent spectroscopy? To say something reasonable about it. And not just be sad because you don't have 2D Fourier mixing, 2D Fourier spectroscopy experiment. What can you do? Measure the line widths, exactly. Yeah? With line widths, again, one needs to be careful because the line width is a combination of many factors. But if the line width goes down to a very small value at temperature, then you can use the temperature-dependent line width as a proxy for the scattering rate. And there are a few things one needs to consider, that the phase scattering rate does not always have to correspond to momentum scattering rate, but this goes a little bit too much detail. But in principle, one simple analysis you can do, you can take dephasing from scattering rate. How do we get the mass? How do we get the mass? Mass is tough. Yeah. Who's here from Wrocław? Oh, here. How do we get the mass? Magnetic field, what do we need to do with magnetic field to get the mass? Diamagnetic shift, exactly. And if you don't have experiment, but you have literature at your fingertips, then you can, exactly, then you can go to some form of band structure calculation. Typically, of course, that I may be corrected tomorrow, when you have Coulomb renormalization, typically the masses are not affected. In many cases, the band shifts apart. There are other contributions to the mass if you think about polaronic effect, but in the simplest approximation, you can take the sum of the electron and hole mass to get a feel for diffusivity in the semi-classical model. And this is an example how it comes out for the case of 2D perovskites. Yes? That in principle, you can get reasonable agreement, which, by the way, does not necessarily mean that this description is correct. It just means that if these parameters independently inserted like this, then semi-classical drift diffusion model could explain the experimental data. But there's one thing that we need to consider, and this we will do after the break, is the applicability of the semi-classical description to begin with. Yeah? And I want to leave you with this for now. This is where we'll start. We'll try to make maybe the second half a little bit shorter. When can we even apply the semi-classical picture of exciton or even electron propagation? Okay, so I would suggest we do 10-minute break, and then we get back to this. Okay, thank you.
Excuse me, if you don't mind, can we go back to the lecture? I will, excuse me, can we go back to the lecture?
I try to do something like 40 something. Okay, wonderful. Welcome back. I want to finish up this part of the propagation modes with the following. And this is something that is known for electrons, and this is something that we need to consider every time we describe a quasi-particle, which is quantum mechanical, in a semi-classical description. Right? That the moment we have this type of picture, that we describe a quantum mechanical quasi-particle in this drift-diffuse motion, what we usually implicitly assume, and this is a so-called Motyoffa-Regel criterion, that, okay, if I would be a quasi-particle, so if I am an exciton, it means that my mean free path needs to be equal or larger than the size of my wave packet. Yeah, this is this thing. This is the de Broglie wavelength that determines the average size of the quasi-particle. Here's the mean free path. And if this is true, if your de Broglie wavelength is smaller than the mean free path, then the semi-classical description makes sense and is applicable. And then you can treat your quasi-particle, your excitons, as basically a classical particle with a mass. On the other hand, right here, if the opposite is true, yeah, if this would be my de Broglie wavelength, and then my mean free path is like this, then this description will break down. Yeah? And quite interestingly, a lot of semiconductors that people are studying these days, especially the fundamental materials, so the transition metal like alkylgenide, the perovskites, the de Broglie wavelengths are roughly in the range of mean free path. So it becomes even questionable, a little bit also to the discussions on the side, whether this drift diffusion approach is even applicable. Yeah, and which means that certain transport phenomena needs to be calculated more accurately and not using this simplified semi-classical models. And then hopping, of course, also doesn't help us because we are in this intermediate range. Just to mention very quickly, the phenomena that one expects there, and something is very well known in electronic physics, it's called weak localization. What can happen if your movement of the exciton, the mean free path is smaller than the de Broglie wavelengths, an effect which is called quantum interference can occur in a simple way. One imagines like this: the exciton would technically take the same path from two different directions. If the relative phase is not lost, then it will localize for some time in space due to this phenomena. Yeah? It's a very simplified picture, and as you can see, for the excitonic prediction is 98, and then there is a recent paper discussing this for two-dimensional materials. There are observables, such as comparing classical diffusion as function of temperature with the one that takes quantum interferences into account, and there is some experimental evidence to this. Yeah? It doesn't match in terms of numbers, so one should not call it weak localization, but what it shows is that also in the experiment, the semi-classical transport, so the actual transport can deviate from the semi-classical prediction, and also, as you can see, is not hopping, is not temperature activated, which means that taking the quantum mechanical nature of the exciton into account beyond the semi-classical approximation can be relevant for a number of systems under study, and it's not an easy theoretical problem to solve. And with this, we're done with this part, all in kind of linear regime in terms of exciton density. However, what can happen very quickly in experiment, you know, everybody of you who's doing optics in particular, you can always pump it harder, and sometimes even pumping gently already brings you into nonlinear range, and the diffusion can become nonlinear, which means it changes with density, and also anomalous, which means the deviation of this linear increase of area over time can occur. And one example is a very simple system, definitely subject to disorder. Again, monolayer, room temperature, and here you see measured diffusivity as function of pump. For those of you doing ultra-fast experiment, nanojoule is already very gentle application of optical power. This data that one would get is similar for freestanding, so the substrate itself doesn't matter much, and there is almost 100 times increase in effective diffusivity at room temperature. And in principle, you can take it as, okay, wonderful, so we have a way to make excitons faster. However, we need to remember one thing. What distinguishes excitons from, for example, molecules and other particles is, or even hydrogen atom. Yeah, if you think about exciton and hydrogen atom, what is different between exciton and hydrogen atom? What is different? Mass is different, sure. Else, what else? The electric constant, sure. I mean, these are the things we learn in lectures. And then third things, even simpler. Dimensionality, maybe, yeah, but we also have 3D excitons. Yeah. What else is different? Do hydrogen atoms recombine normally? No, right? There is the number of particles conserved. For excitons, the number of particles is not conserved. And this is something to consider also with respect to electron transport measurements, that the exciton lifetime is finite. And the changes of lifetime, and this is what I want to show you, are important to consider transport and optical transport experiments. They're important the following way. The lifetime here, as you see, decreases quite strongly with increasing density. The total luminescence is nonlinear. Yeah? It saturates at higher densities. And Bose's observation are a sign of a phenomena. This is very well known in semiconductor physics. For electrons, it's sometimes called Auger effect or Auger-Meitner effect. The same occurs for excitons. This is schematically shown here. If two excitons meet, this meeting can be not, they can form a biexciton in certain conditions, but also there can be the consequence that one exciton recombines non-radiatively and gives an energy to another exciton, which maybe is even ionized, right? So there is a non-linear, non-radiative, so density-dependent non-radiative process for excitonic particles in many, many material systems, including two-dimensional semiconductors. It's sometimes called, this is a little bit more from maybe nano community, organic community, exciton-exciton annihilation. And the consequence of this annihilation is relatively straightforward. If you have a distribution of particles and you have density-dependent nonlinear recombination, so the more particles you have, the more they annihilate, then what will happen is, as you see here, in the middle when the density is high, this density will decrease faster than on the flanks. Yeah? So your Gaussian distribution will morph into something like a flat top without anything diffusing. Yeah? So your shape of your distribution will change over time, and that will give an effectively measured increase of diffusivity without actually meaning that the transport is, in fact, faster. Yeah? Just because the shape changes, so distribution becomes broader because of this effect. If one wants to model it, this is one way to do it, to add an annihilation term in addition to the linear recombination. Yeah? And in fact, as you see on this reference, this is something that is known also for bulk materials. So this is an example for cuprous oxide where this process takes place and where exactly this effect can be observed. In this particular case, one can also make some quantitative estimation how it should be for the measurement. What also can happen is that these excitons that are created have excess energy. You have additional phonon wind or drag, so you have expansion of, for example, phonons or even hot excitons from the middle of the spot. And if this effect is strong enough, it will lead to something quite unusual and occasionally observed also in quantum wells for gallium arsenide, but also here, that the shape, this Gaussian shape of the exciton distribution can even morph into a ring because the excitons are pushed out from the middle. Yeah, this is a more extreme case of exciton-exciton interaction. Now, a measurement that has this phenomena, for example, that shows this phenomena, will then show that the area does not expand linearly, because in the beginning, it's dominated by annihilation, and then towards the end by linear diffusion. Okay. Now I want you to consider an alternative explanation of this type of data. If you see something diffusing very fast in the beginning and very slow later, what could also be the case? And indeed it is in some materials. What can also lead to something like you're fast initially and then you're slow at later times? Something we even partially discussed. Yes? Sorry? Heating up, yes. So if you have a transfer of energy to the lattice and then you have increased scattering, yeah. But let's say for the sake of argument that the lifetimes we're talking about are much longer than the transfer of energy. But in principle, yes, this is possible. What else? Repulsion, we'll come to this a bit later. Repulsion, that definitely can occur. So if the excitons repel each other. And then again, think about material which is not perfect. Real material has, what does it have? Defects, traps, right? So what can happen, and this is an example for perovskites, that the opposite is the case. In the beginning you have free diffusion. So in the beginning, the first nanosecond, this is where the free diffusion takes place, and then increasingly the exciton distribution becomes localized, and then you have the super sub-diffusive behavior in the temperature, in the time dependence. Even more extreme, you can sometimes observe contraction of the exciton spot. Yeah. What would violate the term negative diffusion? Which fundamental principle would it violate? Why do not things contract? Why it cannot be negative diffusion, which can just call it like this, but why not? Entropy, yes? Entropy. What about entropy? Let's have a student answer. What about the entropy? If the exciton distribution will contract instead of expanding, what does it mean for entropy? It's getting smaller, yes? It is as if, okay, I have a bad example, I will not bring it, but imagine a certain amount of particles released into the air locally, they will disperse, and everybody will notice. The opposite is unfortunately cannot happen, right? I mean, it's the same reason here. The excitons cannot contract. Don't laugh, it's not what you think it is, the example I gave. But this is observed, and usually when you have something like this, you can again imagine excitons now not repelling each other, but attracting to each other. This definitely can be a model explaining this type of observation. But even simpler, what can happen is, imagine the following, you have two components. Again, think about localization. You have a component that expands very fast and is short-lived, and you have a component that doesn't move but is long-lived. If you have a situation like this, a two-component diffusion, that will quite often lead to such very unusual anomalous diffusion phenomena. So you have an expansion and apparent expansion and a contraction of the exciton cloud. But again, what it means is that after some time, the quickly dispersing fraction recombined, and then what is left is a long-lived fraction of the excitons. Yeah, just to show you an example of something more extreme in terms of change of the area. And then we come, we're good on time, to heterostructure. This is the last part. We're almost done. We'll have barbecue shortly. But heterostructure is quite important. And heterostructure, as you know, is by no means limited to, let's say, more modern versions of it. You will hear also during this conference, as I saw the program, quite a bit about van der Waals heterostructures, but heterostructure have a long history. Yeah? For example, there's a Nobel Prize given to these researchers for superlattices and quantum wells. This is where you find, this is a classical example of a heterostructure. This is something we use in technology nowadays every day. Lattices like this. Or organic blends is another example. Yeah, you put different types of molecules, you have a charge transfer excitation. So again, bringing materials together is something that will not be a surprise to any of you. That this is one way forward technologically if we think about designing matter. For van der Waals materials, so for example, you have a situation like this. The platform offers a few, I would not necessarily say advantages, maybe advantages, but a few additional aspects. For example, typically for van der Waals system, the lattice matching requirement is very much relaxed. So you can turn and twist and change lattice constant and still bring materials together. And yes, this is PowerPoint physics, but something like this is shown, has been shown many, many times in reality, STM, FM, as you wish. In these systems, they're not only this type of indirect excitons, but also, and this is something that you will hear from Kim van Mark on, I think on Tuesday, physics related, how excitons can be used to measure correlated states. I will not explain this plot here. It will take us another couple of minutes. But what it means in the end is that if excitons are sensitive to external screening, then one can think about much more than just the effect of the static screening. You can now think about screening from a correlated or uncorrelated states that lives in close proximity to the exciton gas using excitons as sensors. Again, you will hear about in a couple of days. But all of this motivates, and in additional predictions for some topological states on the edges, motivates that people have been looking quite closely into exciton properties and also exciton propagation in heterostructures. Okay. Generically, if you think about, we go from a monolayer material to this hetero bilayer. What would you expect in transport, intuitively? You say, okay, what is the expectation? Maybe even based on this picture. What could you expect? Faster or slower? Or is it even a sensible question to ask? Opinions? Faster or slower?
Slower. The charge separation increases.
Yes, and then you may have longer lifetime. And then you may have longer lifetime, but that doesn't necessarily affect scattering rates in transport. Yeah. In a Moray system, what would you expect? System like this on the left, we have local minima. What would you expect there? Hopping, localization, thermal activation, potentially slower transport. The more surprising it was that in one of the early measurements, and this is from the lab of Li Bai Huang, the opposite was observed. And the system is complicated. It's not necessarily universal, but in this observation here was that interlayer excitons can actually be much faster than monolayer ones. And one of the ways to think about it is the following. We discussed about this process. We discussed about annihilations, about this recombination. What else can you expect here? Even just from very classical picture without thinking about short range and quantum mechanics. But classically, what would you expect if these excitons interact? What is not shown here yet? If you have two dipolar excitons coming close to each other, what do they feel towards each other? What do they feel towards each other? Attraction. Two of those come close, negative, positive. They will repel, exactly. They will feel repulsion. This, Yes, but for biexcitonic state, you actually need it's hard to build a biexciton state from these two dipolar excitons. But the repulsion, it can be not trivial to handle also theoretically, because usually one also need to go beyond this classical description, but in principle, it is the case that in this case you can expect, again, a density-dependent term, which will give you a current of the excitons due to the repulsion. And this indeed was observed, or the data was interpreted like this. Here, from bottom to top, the density increases, the diffusion becomes more and more subdiffusive, much more faster and faster in the beginning, and then towards the end, towards the later times, you get back to linear diffusivity. This is another way to look at it. This plot shows the extracted diffusivity for different densities. It's a little bit complicated, but in the end, what you also see here, the higher the density, the faster the excitons, and then in the linear regime, they are quite slow. And in this linear regime, you also see this temperature dependence, which means what? Semi-classics are hopping. Sorry? Hopping, exactly, hopping. Very clear. We start with very low numbers, and then there is the temperature density activation. So slow excitonic diffusion. And here, and this is the last part, I want to show you one example how I can look at it. Building a heterostructure, which in this particular case, for certain reasons of what is called atomic reconstruction, so that the lattices can actually arrange if the angle is very small, so you combine two lattices, that you don't observe Moiré patterns, but the system basically goes into a single registry. And in this particular case, the system can be quite simple. So there is this interlayer excitons, this charge transfer you see in luminescence and in reflectance. There is no evidence of Moiré. This slide I will skip. This is for people who are working with heterostructure to convince you that this is a specific registry where you can look at polarization, at G factors, at energy positions. This is at this point well understood. And then we go to transport and we see again something semi-classical. The diffusivity is high. The numbers are 100 to 1,000 times higher than you will have on Moiré. And as the temperature is increased, the transport either constant or starts to decrease. And we have a lifetime that is short, right? We have a heterostructure with a nanosecond lifetime. And this is important to consider. And I will not tell you anything, too radical by saying that, well, the coffee machine disagrees, that if you think of what you said, right, radiative recombination, this is an argument you will hear a lot, and the argument is not incorrect, that if you go from a monolayer exciton to this type of exciton, that the radiative recombination is suppressed, right, because the wave function overlap is smaller. We would all agree. However, if you have a system, and most realistic systems do have non-radiative channels, these channels do not magically disappear just because we start and build a heterostructure and increase the radiative lifetime. They're still there. Which means that in many cases, when you go from single layer to a bilayer, and you observe your lifetime changing from hundreds of picoseconds to hundreds of nanoseconds or even microseconds, it's quite likely, I would not claim that this is every time the case, but it's quite likely that this is a combination of reduced radiative coupling and also localization. Now you get rid of localization, you make the potential flat, you make the exciton moves, and what one recovers here is more or less monolayer physics. Okay? So again, if the diffusion coefficients are high, the lifetime can be short, because again, the excitons are reaching non-radiative centers faster, and this is one of the results here. And regarding the nonlinearity, also here, one can see that the effective diffusion coefficient will increase with density. At some point, there is even a Mott transition, which is a little bit harder to determine accurately, at least in luminescence experiments. And one thing to consider that at this case, if one just looks at the transport, just at the broadening, one cannot distinguish whether it's repulsion or annihilation. One needs to make additional analysis, actually properly count the excitons in absolute terms in the spot. And finally, one can have weird effects here as well, add the Mott transition, expansion, contraction. But I would stop here. It just means that you get highly nonlinear behavior under conditions where you start expecting different contributions from excitons and from plasma. And with this, we would finish on the impact on annihilation, exciton halos, negative diffusion. For heterostructures, I showed you the relevance of exciton-exciton repulsion, nonlinear diffusion, localization, and free propagation. One last example, just because you have a bit of time, just one example. There are materials that are combined magnetic and optical excitation, so a lot of people these days working in the van der Waals field are interested in materials such as chromium sulfide bromide, which is an antiferromagnet, which also hosts excitons. And in this case, also in transport, one finds interesting phenomena such as the actual diffusivity deviating as a function of temperature from semi-classical predictions, which you see here, but instead correlating with the magnetic phase transition. Yeah, and there are additional phenomena associated with this. The diffusion is nonlinear. There are sometimes super-diffusive behavior at 5 Kelvin. But in this particular case, the transport of excitons reacts to the transition from antiferromagnetic to ferromagnetic phase. There is likely an effect such as exciton-magnon drag, but I would stop here just to show you as an example that in magnetic systems, there are a lot of interesting things about exciton transport to be considered and ideally understood. In principle, and in this field, among the open questions and the interesting situation would be mixtures of excitons and electrons. And there are some more trivial regimes where it just adds to the scattering. There are situations where quasi-particles form. There are situations also where you have true polaronic physics and how the exciton transport should be described. Exciton valley Hall effect relates to some symmetry considerations, the van der Waals heterostructure, condensate superfluids. This has a long, long history. I mean, we have David Snook in the audience who probably remembers well all the discussions and maybe even partially controversy about this superfluid behavior in condensates and quantum well systems. Yeah. So about, well, by now 20 years ago. Yeah, but these topics are still very much alive. Exciton Einstein-Bose condensate, superfluidity, and there are people working on it. Leonid Butov is a good example. And of course, we have all these platforms such as exciton transport in the presence of correlated state, which now can be accessed not only in MRA systems. Wigner crystal of electrons are realized in monolayer materials. They can interact with electrons, with excitons. Potentially looking at topological edge states, but this is almost proposal space. And magnetic materials, and I gave you a very quick example of which type of phenomena one can expect there. And finally, again, it's a tutorial, and I hope majority of you will just walk out, have a beer, and never think about exciton transport potentially again. But in case you will, there is a book which is edited by Parag Diatara and Tsaitan Mi, and there is a couple of, well, it's a little bit self-serving, but there is a couple of chapters. One from Leonid, one from Kanagdata and Parag himself, one from us together with Misha, discussing some of the physics much more properly and much more accurately. We have the references. So this is something, if some of you are interested in the optical transport, in the exciton transport, I would recommend. Obviously, it's not a real book, it's online, yeah, but easily accessible. And with this, I'm happy to answer any questions. Of course, we can also talk later. I'll be around for the rest of the evening. Thank you very much. Yeah. Questions, comments, objections? No, you don't need to ask Michał, don't even try. Don't ask me oh, let me start. I know it's your job, but not do it. So, did we have one? Okay, yeah.
Here. Hi.
Oh, okay, sorry, yeah.
Yeah, thank you for the talk. And I didn't understand these plots that had the change of area versus time. How would you understand? Is it like the change of area from the moment we introduce some area of excitons?
Yes, so let me quickly go there. I need to try to remember where it was. No, not here. This plots, yes?
No.
No?
No, a bit...
but this shows change of area over time. Is that plot
okay,
clear?
maybe it's the same, yeah, but I remember with experimental points. Yeah.
So one thing, I was probably a little bit too quick. You see sigma square as function of t minus sigma square 0.
Okay.
up here. Sigma square 0 means this will be your initial size of the spot, given by the size of the laser spot on the sample. Yeah.
Okay.
So in this case, in principle, in most cases, people look at the changes at the delta of the area. So we not start with area 0 in this case, as a rule. Yeah, we start with something finite. And then it increases, or decreases, or stays constant.
Okay.
Yeah, I mean, like you put a drop of color in the water. This drop has a finite size.
So
It's
if,
not 0. And then the size grows, and you analyze it.
So if on this plot the slope is negative, it means that the growth is slowing down, right?
So, well, again, this negative part needs to be taken with care because it doesn't need to represent the actual contraction of the exciton cloud. Yeah, so if you're looking at the data like this one, in this particular case, what you actually see, first of all, again, this is a change in the area. So the 0 is not 0. 0 is you start with a finite laser spot, and then what here you initially observe very fast expansion, and then it looks as if the spot contracts.
Okay.
Yeah. But in this particular case, much more reasonable model is that those who were diffusing fast, they had a short lifetime, and then you end up with some localized fraction.
Okay. Yeah. Thank you. Now it's clear.
Okay. Yeah.
So if we compare the kind of classic semiconductor quantum well with the 2D systems, what do you think is the kind of biggest new thing you observe? I mean, I guess the moire, but what else is there that's really different in the 2D systems that wasn't present before in the like indium arsenide, gallium arsenide, or other quantum wells?
Let me think a little bit how I answer it. That's not typically a question I would get from students in the summer school, but it's obviously a fair question to ask. One difference to begin with is you can consider as quantitative, that the binding energies are larger by orders of magnitudes, which means you are easier reaching conditions that were very difficult for quantum wells. Yeah, so you have higher number stable complexes, you can observe even bound five particle states up to relatively high temperatures. In addition, in some of the systems you have the so-called spin valley locking, because the excitons live not at gamma valley but at K valleys, and there is possibility to impact valley polarization, which in gallium arsenide you would not have access to because everything happens at gamma. You can mix and match materials, so heterostructures is a big deal, for sure. And then one very pedestrian answer to this question is, if you don't care about excitons, and maybe you shouldn't, but anytime you try to explain optical experiments or build an optoelectronic device, one needs to understand how they propagate. Which doesn't necessarily mean that we rediscover something that was not understood for classical quantum wells. Think about exciton-phonon interaction. But it means we need to understand it in this particular system, with these parameters. Yeah, and then you can have all sorts of versions in perovskites. You have polaron physics. You have very strong coupling with phonons. You have new quasi-particles, and you have, yes, in the end, you said it yourself, all this business of looking at correlated states, which is not impossible. People did, again, measurements of superfluidity, claimed condensation. But for this, of course, it's useful to have a platform which is much more tunable. Yeah. But again, the purpose of this talk was not necessarily to try to convince anybody here to work on the mass materials and that they're better than quantum wells or anything. I mean, I grew up with quantum wells myself, just to have it as an example. Yeah.
I ask a question about, you mentioned about the repulsion term, right? Can you describe a little bit, because that goes very fast.
So, yeah. So the repulsion term will be proportional to the density of the excitons locally, and it will be proportional to the whatever you set in here for this U, yeah, for the interaction between them.
Okay.
Yeah, and then you can unpack how how it's written out explicitly in the equations. But in the end, what it describes is if excitons come close together, there is a distance-dependent interaction which is repulsive, and that enters the diffusion equation like that.
So in the experiment, what's the signature of that, for example?
So in the experiment, the signature would be, first of all, that you have a faster expansion in the beginning than at later times. However, this is typically not enough because also annihilation will produce you this type of data. So one would need to look for, imagine I'm measuring some arbitrary units, but the absolute counts, okay? So in case of annihilation, you would expect this. In case of repulsion, you will actually expect that on the flanks, you have more excitons than you had before. And this is observable, that you actually see that you have an additional current. So where the intensity of PL was low, now after some time is high. And then you can, of course, also quantitatively analyze it. Yeah. But you need to observe the actual current in some version of it, not just the change in area. That would be the answer.
Okay, yeah, here. So thank you for the talk. I've got a question about the Wigner crystal regime. So what exactly changes? What happens to the excitonic transport when we go into this regime?
Well, obviously, I mean, I gave you zero chance to understand it because I didn't say anything about it, right? So, so right now, I give you a quick answer, and then if you're interested, I can give you a reference. Yeah. So when the excitons, first of all, when you have an additional crystal superstructure, like a Wigner crystal, your exciton band structure is a little bit like with Moret. You have band folding, you have something like a mini bryon zone, yeah, and you have, let's say, excitonic states, which the exciton dispersion is not like this anymore. Yeah, but you have backfolding here. When you have interaction with the Wigner crystal, then something similar happens as what we learn in semiconductor physics in the real band structure. Then you have some gaps open up and the effective masses of the exciton change. Yeah, and under certain conditions, you can expect slowing down of transport. But again, for me, it's a little bit hard to explain it in 3 sentences. But in principle, and this is a theoretical expectation, there is zero experimental data for this. That's why this is an outlook of sorts, right? That one can now consider correlated states of electrons. Yeah. But one of the expectations is indeed a slowing down of transport that will then depend on the density of electrons and on the spacing of the Wigner lattice. Yeah. Or write me an email, I'll just send you a link to the theory, and there it's much more accurately explained.
Yeah, thanks.
I have a...
I'm sorry.
Conversion application, like for example, photocatalysis or photocatalysis. We need the material have a long like length and like more diffusion, and also we need high low exciton binding energy, like a long lifetime of the exciton. And so what we are studying, or what you present here, is in the monolayer and also in the heterobilayer. So my question is, how about the case if we extend this to for the energy conversion application? As I say, we need a large area or more length, but when we increase it, and we want to like a long diffusion. But so when we increase the diffusion, then the recombination will be high, as you here present. So how to control this issue?
No, but this, okay, so first of all, I mean, I have zero expertise in photocatalysis and what's not. So the point I wanted to make is not that it is per se inescapable to have fast and long diffusive carriers. It was just to say that in a system where the diffusion is increased, the recombination sometimes happens much faster because these non-radiative places are reached. Yeah? But in some of this implication, the same as for photovoltaics, it ultimately comes down also to the quality of the material, to the number of these non-radiative sites to begin with, which is more of a question towards synthesis and material treatment rather than, let's say, fundamental exciton physics. Yeah. So in this particular case, if we would want to have, let's say, fast diffusion with HBN in this particular case, and still long propagation, or long lifetime, one would need to actually reduce the density of non-radiative centers. And there are versions of it. People use flux-grown methods, some particular treatment of materials, but it is more on the material engineering side rather than on the excitonic physics side. Sorry, it's a very long answer to get better material type of response. Yes, I'm sorry. Yeah. Okay. That was, I think, a question.
Yeah, I have a small question. What about magnetic field? Does it provide any instrument or tool to study behavior of exciton, and does it provide any additional information about them?
Let's say if we don't consider the transport aspect by itself, then yes, of course, definitely. I mean, you have the classic application. You look at the Zeeman splitting of excitons, for example, to identify states, or you look, what was also mentioned here, at diamagnetic effects to find the size of the excitons. Exciton transport in the presence of magnetic field is something which is not very well explored. However, of course, and this a little bit couples to the question of why is it even interesting. I mean, I'm rephrasing what you said in a Russian way, but it was basically this, right? I mean, the challenge of, okay, what is actually interesting about excitons in the system? If you consider the magnetic materials that I showed you here, where you can switch the antiferromagnetic to ferromagnetic behavior, and you have excitons interacting now not with individual spin, so we're not talking about gallium arsenate doped with magnesium, but we have a genuine magnetic material that now you can study the impact of magnetic phases on the exciton transport, for example, in this type of experiments. And if you ask me about expectations, then I will do the typical experimental physicist eject. We know that exciton interact with magnons. We know that something happens in magnetic phase transition, so hell yeah, we will look at the exciton transport in magnetic field, okay? And then somebody else will understand it. And we first have to see if there is an observation. Yeah, but this is one of the directions that is now possible to take with these particular systems in the magnetic fields. But ask me in 5 years, yeah. Setup just started working last week. Okay. And I mean, there are certainly other people doing it as well. Okay, so, yeah. Yeah. But this was also a good example. I mean, you want, yeah, also towards your question.
Okay, I have a last question, right?
No, there's one more, but we'll go to drinking and eating soon. So.
Okay, I have a nasty but quasi-student question. So if we have this diffusion and transport, which is so impressively low, how we can increase the distances?
Sorry,
sorry.
Say again.
How you can increase the distance of exciton propagation? Right?
The distance?
Yes. Now we have a micron.
Oh, no, this is not nasty at all. I was already bracing for something. The distance itself, again, in many cases, is determined. Let's say if we talk about free diffusion. Okay, if we talk about free diffusion, it will be still the function of material quality, because in many, many cases, realistically, the lifetime is what limits the distance. And some examples, if one looks, for example, at organic semiconductors, I didn't give those examples here, but of course it also has a very rich field. In tetrazine, for example, people shown that the excitons can diffuse by many micrometers. It just happens over microseconds. Yeah, so the transport is relatively slow, but they go far. If you have high mobility, then of course you apply, external field, and then you can have drift currents over microns, but also there, the moment the exciton encounters non-radiative states, that will limit the transport, and this is very similar. And maybe last part is, of course, if we have a bright exciton state, which recombines very quickly, this would be a problem to begin with, because then we'll have a natural recombination channel, which means if you want to have long-range transport, we're better looking for a dark state, for exciton that not emit light very quickly and very rapidly. Yeah. All right. There is one. Yeah.
So I have a very short question.
Yes.
But here you showed during your presentation mostly the propagation of neutral excitons.
Yes.
But can you observe diffusion of charged one, or are they too sensitive to some disorder to observe any movement?
Sorry, I didn't want to turn my back necessarily to you. Yes, indeed, such type of experiments is possible. I was lucky with the slide number. What you see here is diffusion of excitons in the presence of electrons. This is a field effect device where you externally can tune free carrier and in P and N regime. And very quickly, what you see in this figure, this is, by the way, not singularity at zero. This is an actual, it doesn't diverge. Yeah, you just reach a phonon limited case. Initially, in this regime, you add more electrons, excitons scatter with electrons, the diffusivity decreases because you add a scattering channel. Right here, where this curve becomes non-monotonous, you start to have trion formation. So you start to have a formation either of a trion, which is a three-body state, two electrons in a hole, or you can think about it in the form of a polaron, like a Fermi polaron, that the exciton carries the polarization of the electron of the Fermi. And in this case, again, as we have quite often in physics, when what was treated perturbatively before is now a new quasi-particle, now the interaction of the trion with the remaining electrons is suppressed. Yeah. And one way to think about it, if you have electron and exciton, they can come very close, interact with exchange. If you have a trion, it will repel the electron due to long-range Coulomb, and the scattering is very inefficient. And this is, by the way, a result that the scattering of electrons with trion is inefficient, is known for a long, long time. From quantum wells and zinc telluride, I think, in 2000s, people knew it. And here it leads to the recovery of the transport in this unusual case. Okay, this was a very, very quick explanation of it. But yes, it is possible, but it not, again, also broadly explored in all sorts of conditions of phase space and what's not. But yeah, for sure. You get trions and you look at how they move.
Yeah, thank you.
Yes. So.
And does it change much when you apply a magnetic field?
We have not applied magnetic field. Yes. Hopefully, maybe. Yes. I don't know. No. So again, I mean, the question maybe one last remark. For the field of electron transport, we know from probably more than half a century that electron magnetotransport is understandable. This is almost an unexplored space. Yeah, people did some of it, a little bit, but there is no established exciton magnetotransport yet. So the consequences, it may be a good idea to do it. Yeah, a little bit along the lines of your question. Okay. Is it a good statement to stop? Yes?
Yeah, so let's find
okay,
the speaker.
thank you.
Yeah, so let's find
okay,
the speaker.
thank you.